This whole unit this morning.
What'd you say? Tomorrow we got family pictures. Then we're gonna go to Mariola's and then Annie. So like it gets better throughout the evening.
2/3
Yeah.
exponential work.
At Mariola's tomorrow night? Okay, cool. Yes.
Like line paper too?
Not for today.
Okay, just this.
Just this for today. The goal would be to finish this, but I don't think we will. Those video announcements took a little longer than I expected. We've also used like half the time we have. That's okay though. Okay. So here we go. Chapter 8 is called bonding.
What chapter?
Chapter 8 is bonding. Chapter 9 is also bonding. Okay? So we're doing a lot of bonding over the next two chapters. You may think you know a lot about bonding, but you have so much more to know. So much more to know. So
Can you review what Coleman is?
we're going to review.
Because I don't even know what that is.
We're going to review. So we're going to start out with intramolecular bonding. When you hear of intra, what does that make you think? If you are doing intramurals, right? Intramurals is like within, right?
Oh, yeah.
Right? It's not between, it's really more within. So this is within molecules, between molecules, but it's all based on what?
Bonding.
Guess what this is all going to be based on? Yep, there it is. Coulomb's law.
Mr. Coulomb.
Mr. Coulomb's law. So, the main types of intramolecular bonding is ionic. Ionic bonding happens by what? Transfer of electrons. That's the transfer of electrons. Remember how we would like draw arrows, right? Here's Na, here's Cl, 1, 2, 3, 4, 5, 6, 7, right? Yes? I just did that with my freshman yesterday. Covalent is what about electrons? Sharing is covalent, yes.
Sharing.
Covalent is sharing of electrons. We'll draw some of those more. And a third. So they're not all ionic, they're not all covalent. In fact, most of them are neither. It's wild. So, I know, you're like, what? Everything I've learned so far is false. Yeah, you're right, it has been. So, let's review. First, electronegativity. What is electronegativity?
How easy it is to gain.
Yeah, the ability of an, let's say, atom to attract an electron. So, when we're looking at an electron cloud diagram, it can be thought as kind of like a probability map, where an electron might be found at one time. If they're separate atoms, it would look something like this. Here's atom 1, here is atom 2. Are they different atoms?
Yeah.
How do you know?
Different colors.
Different colors. Are there electron clouds that different though?
No.
No, they're about the same size. Yes?
Yeah.
Okay, so when those atoms join to form a what? Covalent bond. When these join to form a covalent bond, a pair of electrons is shared. Each atom still has its own electronegativity. Each atom still has its own electronegative. Oh shoot, I ran a room. Sorry. Which increases from the left to the right on the periodic table, which is not a good answer on a trend question. That was not the right answer on a trend question. The right answer was define the trend. It was talk about, it wasn't, if you just said increase, up, down, or left, right, that got you no points. I can't tell you, Ella hasn't taken it out. On the trend questions, remember how I taught you how to do it? You have to define the trend.
Yeah, 1, 2, 3.
You have to define, you got to talk about net nuclear pole, shielding. Anyways, if you just said goes left, up, if it increases left to right, that's not.
Can we get a third because that's one of the 1, 2, 3?
I'm going to give you a point. Okay. Anyways, increases left to right of the periodic table and from the bottom to top of a group. Bottom to the top of a group. Fluorine is the most electronegative element, right? Fluorine wants to do what vigorously with one electron? Ooh, vigorously. I know. Gain, right? All right. Low level amount, low shielding, right? And in that column, in that period, it has the most what? Core charge. Has the most core charge. Okay, so if a pair of electrons has basically the same electronegativity, all right, they will equally share the electrons. An electron cloud would look like this. Open up your book to page 306. Page 306.
Thing is that 8.8.
What? 8.3. So on page 306, here is a chart of all of the electronegativities. These are all the electronegativities. Is that something to memorize? No. All right. So, do you see how my electronegativity changes? Yes. You see that chart? Yes. Okay. So, if they had the same electronegativity, it would look like this. This hardly ever happens. In fact, it barely ever happens. If they're going to have the same electronegativity, what would you have to do? Look at this chart. How would I get two things with the same electronegativity that bond together?
They want to gain the same number of electrons?
Let's keep moving.
It's the same thing.
Yes. It's the same thing bonded to itself. You got it. Yes, exactly. It's the same thing bonded to itself. This rarely happens though. You only see this in diatomic molecules. You only see this in diatomic molecules or sometimes hydrocarbons, right? But diatomic is the main thing. These are also non-polar molecules. What does non-polar mean? They have an even distribution of charge. They have an even distribution of charge. What would that look like? If you flip it over to page 309, on page 309, is this molecule polar or non-polar? Non-polar. All right, it's equal. And I don't want you to get confused between polar and non-polar. It's like you can split it in half. All right? Splitting it in half does not mean it's non-polar. It just means that there's an equal distribution. Whereas water, is this polar or non-polar? You can see it, right? But down here, this is SO. Oh, I can't even get it on the page. I'm gonna try to zoom out a little bit. Yeah. Almost there. Almost there. I can't even get there. All right, SO3. You guys can see that on your book, right? I know. Can you split this in half? No, but is there an even distribution of charge? Yes.
So does that mean it's polar?
Non-polar. Non-polar. The one in the middle? Hydrochloric acid? Polar. Definitely not evenly distributed. Right? Because we're looking at the charge. Does that make sense? Okay. Because one of the major misconceptions, I would say, how teachers teach this is, well, if you can cut it in half, it's non-polar. Well, that's not necessarily true. Not necessarily true. So, many times, one atom has a much blank electronegativity. Let's just say higher or different. Has a much higher electronegativity than the other. So, electrons are attracted to the what? More or less? More. Electrons would be attracted to the more electronegative, right? Because electronegative means they want to grab them. They want to grab them. Leading to an electron cloud looking like this. So we have a less electronegative side, which is more positive, and a more electronegative side, which is negative. That makes sense, right? Yes? Okay. So the atom, I got to zoom out a little bit, with the higher electronegativity will develop a partial negative charge. So the creation of opposite charges at either end of a molecule is called something new. Dipole. Dipole. Put a star by that. It's really fun to say that fast. Say it over and over fast. Dipole, 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 dipole. Isn't that fun? Dipole, 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 dipole. That's not fun? I think it's fun. Dipole, 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 dipole. Okay, all right. And this bond is now considered to be what? No one knows. Polar covalent. Yeah, because I haven't told you yet. Polar covalent. Now think about that. That's weird, right? Because up till now, polar stuff have been what type of elements? What type of bonds? Ionic. Positive, negative. So I'm saying that this is polar, but they also share electrons. Do you see how that's kind of both? Yes? This would be called a dipole moment sometimes as well. It would be called a dipole moment. Dipole, 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 dipole. What? In a second. It's coming. It's coming. I'm glad you asked. Check this out. More on covalent bonds. All right? So each share a pair of electrons forms a single pair of electrons. 2 pairs are double, 3 pairs are triple. So you can have a single bond, a double bond, or a triple bond. Did you guys talk about that all in chem last year? With me, you did. All right. Audrey's the only person who had me for chem, which is weird. Because then you skipped a year and then came back. Anyways, so hydrogen has how many valence electrons? 1. So I bound this with another hydrogen which has 1 valence electron. How many does hydrogen want to have? I also don't know why I wrote that not centered. Wants to have 2, right? Because the first shell can hold how many electrons? 2. So if it has 2, it'd be a full outer shell. So Danny, they share those 2 electrons. Yeah. So this would look like H bonded to H. 1 dash is 2 electrons. 1 dash is 2 electrons. Oxygen has how many valence electrons? 6. I'm going to draw these a little bit weird. 1, 2, 3, 4, 5, 6. Do either oxygen atoms want to donate? No. Because if this donated one, what would I do to this oxygen? I would make it actually less, right? And what they both want to get more. I share a pair here. Now they both technically have how many? 7. Because you count in the pair. So I have 1, 2, 3, 4, 5, 6, 7. So once I share 1 pair, what have I done? How did I teach this originally freshman year? Poke the bear. Thank you. Yep. Share another pair because I say it over and over and over. You poke the bear. Yes. I share 2 pairs. How would this look? Oxygen double bonded to another oxygen, with each oxygen having what are called 2 lone pairs. That's a lone pair, that's a lone pair, that's a lone pair, that's a lone pair. Lone pairs are just, that's a lone pair. Lone pair of electrons. Just by themselves, not bonded to anything else. They're just chilling. Nitrogen has how many valence electrons? 1, 2, 3, 4, 5. So here's another nitrogen. 1, 2, 3, 4, 5. So how many is nitrogen going to share? How many pairs? 3 pairs. 1, 2, 3. What type of bond is this going to form? Triple bond. Nitrogen triple bonded to another nitrogen. Do you see how these are perfectly nonpolar? Because there's only 2 that are not bonded, right? So these lone pairs are not part of a bonded pair. Are you guys okay with that? Do you see how these are perfectly nonpolar? These are the only true covalent compounds. All right? Everything else is not covalent. All of these. Diatomics are your true covalent compounds. Carbon dioxide. Carbon has how many?
There's 4.
4. So 1, 2, 3, 4. Oxygen has 1, 2, 3, 4, 5. It's going to be weird how I have to draw this. I'll draw like that. I'm going to put another oxygen on this side. 1, 2, 3, 4, 5, 6. I'm going to share a pair here with that oxygen. I'm going to share a pair here with that oxygen. I'm going to share a pair here with this oxygen. share a pair with that oxygen. Is everybody happy? Does everybody have a... You tell me. Yeah, they do. So this is carbon dioxide, carbon double bonded to an oxygen, double bonded to an oxygen. Each oxygen has how many pairs unbonded? 2 lone pairs, yes. Each have 2 lone pairs. So, does that make sense?
Yeah.
Okay, good. Covalent bonds occur between atoms with similarities in electronegativity, usually between 2, that should say 2, TWO, 2 nonmetals. The attraction between 2 atoms makes them increasingly stable, giving them lower and lower what type of energy? Oh, we're not talking about ionization energy. If they're stable, they're going to have a low amount of what type of energy? There's 2 main types. Not kinetic, potential. It's stored energy in the bonds of lower potential energies. However, the closer they get to each other, there comes a point when the 2 nuclei, which are what charge? Nucleus always have what charge? Positive, because you have neutrons and protons. So you have positive charge in the middle. Start to do what to each other? You get them closer. What are they going to start to actually do? Repel. They're going to actually start to repel each other. Then, all right, potential energy would be raised. So what does this look like? Flip your book to page number 302. Page 302. It also looks like this. But here's page 302 in the book. Oh, so close. All right? I cannot get this perfectly on the screen. It's the same thing. All right? Here they're too far apart. Right? Now they're a little bit closer. What happens to my potential energy? It goes down. Then right here, boom, that's the minimum potential energy. Guess what happens here? They bond. This is where they actually bond. What? I'm not forcing them to bond. I'm saying this is where they want to bond. Because that's the least amount of energy. But if I push them, this is 74 picometers. That's small, right? I push them closer, right? Less than that. What happens to my energy? It starts to go back up. So this, right here, that minimum potential energy, that is where the bond is actually formed. Does that make sense? Okay. So a happy medium is reached, aka a bond is formed at a distance where the force of attraction and repulsion result in the lowest or most stable potential energy. Because we know when we are bonding matter, the goal is to make it more stable. More stable. Why'd you move? Oh, good. Okay. It's just like so weird to see you so far back.
You don't have a front row.
I feel like I don't have not your presence closer to me. It's okay. Danny moved a little bit
We're
more.
bonding less now.
Yeah, we're like more polar. Yeah. Anyways, that distance is called bond length. The potential energy at that point is the bond strength. The potential energy at that point is the bond strength. Here's what I want you to remember. The shorter the length, the stronger the strength. Ooh. Which is based off of what? Coulomb's law, right? Because the closer the distance, right, the higher the force. See how this all comes back to Coulomb's law? Yes? Shorter the length, stronger the strength. I know. It's almost like I know what I'm doing here. So, since the forces of attraction, aka Coulomb's law, that stabilize the atoms when the bond or attractions between electrons and nuclei, the more electrons involved equals the stronger attraction, right? Because what am I upping? I'm upping the charge, right? Which is the top of Coulomb's law, agreed? Positive and negative. So, triple bonds have how many electrons? 6 electrons. Stronger than a double bond, because a double bond only has 4, and so on and so forth. The shorter the length, the stronger the strength. Flip it. So, yes.
Last time, it was like the less electrons are stronger, or like the higher like the charge or whatever. It's like more stronger, hard to like get them out, 'cause it's closer in. But like now it's the more electrons are stronger.
We're just talking about charge,
Oh.
right? Electrons have a charge too, right? Positive or negative, it's still the same thing. Okay. Once electrons are transferred, the electron clouds now look like this. Cation is smaller, anion is bigger. Does that make sense? Because the anion did what with one electron? Gained. We talked about this. When it gains electrons, they want to repel more. So, how does an MRI work? Look at page 305. I got my first MRI this year. All right, that was a weird night. That was when I had my seizure. I woke up being rolled into the ER, so that's odd. My wife thought I was stroking out, but I didn't. So I'm fine, I'm all good. I'm less than 2 months away from driving again, so very exciting. Yes. So we'll have like the countdown to Christmas break. When we get back, we'll have the countdown to driving, and then we'll have the countdown to the AP test. So anyways, got my first MRI. Who's had an MRI? Lots of people probably have, okay? They put you in this big machines like boom, 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 boom. So what they do is they have a magnet in there. How are the water molecules? The water molecules in your body are how? Polar or non-polar? They're polar, right? Which means they have a positive end and a negative end. So if you have a strong enough magnet, MRI stands for magnetic resonating imaging, right? You line up all of your water molecules, the positive side here and the negative side here. And then all of a sudden it turns it off for a second. And then they form around like an organ. Turn it back on, turn it off. They form around an organ. That's how they do an MRI. It's really stinking cool. It's just chemistry. All right? So all they're doing is they're lining up the water molecules in your body, all right, with science. Water's a polar molecule. Now this is not water. This is hydrogen, like whatever. That's a hydrofluoric acid. But this is how it would work with water. Pretty stinking cool, right? Also, very uninvasive, right? All it's doing is lining up your water molecules. It's not doing anything to you. So, kind of cool. Kind of cool if you understand chemistry. Okay. So, the strongest bonds. The strongest ionic bonds between ions that would be between ions that are either big or small. Small. Why small? Because they're closer together, right? Proven by Coulomb's law. My freshman said it smells like crayons.
No, I smell it
Like just got over here. Like my nose is like cold.
Like they were smelling it and then just like hit me. That's all I can't smell though. It's Hellser.
Yeah.
I think it's Hellser.
I don't smell it.
You know, it's sad when you're.
I've also never smelled anything. So, by Coulomb's law. So, true ionic bonds. If we're going to actually call it ionic, there has to be high differences in electronegativity. Electronegativity. So, really a true ionic bond is going to be between francium and what? Fluorine. Fr plus and F minus. How do I know that? Well, you guys don't have to go back to this if you don't want to. But back in the book, on that page, with all the electronegativities, right? Francium is a 0.7, fluorine is a 4. You cannot get higher than a 3.3 difference, right? Those are the most electronegative. So down here, check it out, right? Down here, ooh boy, these are polar, right? These over here are ionic, yes? In between, it's kind of both. It's kind of both. So as your polarity increases, you get more of a polar covalent bond. Also, same thing here. This chart here. 0 electronegativity difference, it's covalent. Large, it's ionic. Everything else in between is polar covalent. Got it? Is this making sense?
Yeah.
Okay, good. Good. I've also bent my book and I'm kind of upset about that.
What page is it on?
307. is on page 307. Okay, so here we go. Which one, sodium chloride or sodium bromide, would have the stronger ionic bond? If you think you know the answer, yell it out. Well, don't yell, but like. Sodium chloride, that's right. Why? What's the charge of sodium? +1. What's chlorine's charge? -1. What's sodium over here? +1. What's bromine? Are there any difference in charges? No. So if there's no difference in charges, based on Coulomb's law, I now have to go to the size. Which one is smaller, chlorine or bromine? Chlorine. That's why. Try the next two. All right? Which one has the strongest ionic bond between these two sets? Try those in your mind. Strongest ionic bond. Second one's easier than the first one. First one, you can think a little bit more. You now see why we have to understand trends, Coulomb's law, all continually building. Continually building. You guys got it? Or are you still thinking? I'll give you one more minute. Second one's easier than the first one. Got them both? Charge of sodium is what? +1, -1, +1, -1. So can I use charges? No, because they're equal. So I have to go to distance, right? Is NaF smaller or KCl smaller? NaF, right? You'd agree that Na is smaller than K, and F is also smaller than Cl, right? Does that make sense? This is easy, right? +1, -1, +2, -2. Boom, higher charge. You automatically know just from the charge being higher. Cool?
So, why is the first one not the larger ion?
Why is it, what's the question?
If why is NaF KCl, why is it not KCl because KCl is larger?
Well, it's larger. Ionic one, they want to be close, right? Also, these would be farther apart. They would also be farther apart with a greater difference in electronegativity. So there's really two reasons. But also, they want to be closer together. Okay.
Isn't like NAF farther apart from electronegativity than NGL?
Over here,
Yeah.
the charge wins. If the charges are different, charge wins. Always trumps the distance.
Even if it's something like way bigger.
Well, I mean, we're not going to have, you would not have to do anything beyond the scope of this in AP Chem. They're not going to ask you like strontium oxide and like, I don't know, like iron chloride. All right. It's going to be either comparing charge or comparing size. One of them will be constant. What is going on? I feel like I'm missing out on something. Oh, it's really nice.
Sorry.
It's really nice. It's fine. I'm okay.
Just how to get a pic of them.
Of what?
The learning.
Yeah.
Excluding.
They're bonding.
Yeah.
Oh.
Bonding.
How are they bonding?
Ionically.
Looks ionic. What? Toxically. The new bond. The toxic bond. All right. The ions. Has anybody watched it where I've talked like this? Does it get really loud?
I
Not?
haven't missed school one like.
Okay.
There's one.
Okay.
Oh my gosh, I remember on my notes, like two nights ago.
Yes.
Maybe three when I was watching it. I was watching it, all of a sudden I hear you get close to it and you go, Danny is now standing up playing with his Birkin clogs. And I literally wrote in my paper, I wrote Birkin clogs question mark because I wanted to ask about it. 'Cause
Yeah. Someone threw your shoe?
Someone threw your shoe and you were
Brady
out
took
on
off
the
his
foot.
shoe and threw it.
Yes.
And he narrated.
Yes.
Yeah, and you were like,
I don't even know what's happening right now.
Yes. But it was entertaining.
And I didn't see it or anything.
Yeah.
I heard it on the notes and I was like, okay.
Do you think we can finish this page
Yes.
in the next 4 minutes?
Yeah.
Yeah, just write all the answers.
Okay.
We got this.
Well, I want to talk about it. The ions in ionic solids are held in fixed positions in a large 3D structure. This is really important, called a lattice.
Guys, that rhymes with glasses.
All right? That's really, really important. This results in them being brittle. In fact, most of the time this is called a crystal lattice. What does this look like? I'm glad you asked. Glad you asked. We may have talked about that. All right, I got to find mine. Aha. Okay, this is sodium chloride. This is a crystal lattice. All right?
I love that.
What? This is brittle, right? I can literally like crack off pieces of this. These are magnets. Don't lose this. All right, I'll pass this around. But which ones are the sodium? Small or big? The small, because they lose, right? So this is a crystal lattice. I'll pass this around if you guys want to play with that.
Have you made earrings with them?
I have not made earrings with those, but you probably could. So, crystal lattice. What does that mean? So this results in them being brittle. It's held together by strong electrostatic interactions. The strong bonds give ionic solids high melting and boiling points and low vapor pressures. You don't know what that means yet, but more on vaping coming soon. Vapor pressures. There's one missing. So, valence electrons in a metallic solid are considered, this is really important, delocalized. So put a star by this. They are considered delocalized and flow across the atoms. Sometimes you'll hear it called a sea of electrons. This is why metals are malleable. This is why metals can conduct electricity because of this, right? Because the metals flow. They can.
My bad. My bad.
My crystal lattice is now done. The best example of this is alloys. Best example of this is alloys. So there's two types of alloys. You got to know these. One is interstitial alloy. This forms atoms of different radii. So inter is different. Substitial alloy forms atoms of similar radii. And then if you flip it to the next page, you can see what that looks like. You can see what that looks like. It looks like this. Yes. So here's substitutional, here is interstitial, here's interstitial. That, we did it. That's a good place to stop. Good place to stop for the day.